on the next topic. I'm going on to lecture 1, which is on the materials. Those of you who want to follow along may want to call it up. It's called lecture 1, and it should be exposed to you in the lectures area of that O drive. Some people like to follow these along on these slides because then they can go back and sort of check over something that was done earlier. But right now we're going to fire up AnyLogic, and we're going to use it to undertake a task, okay? So what I'd like you to do is to, first of all, start AnyLogic. And just to illustrate how to do this, I'm going to my own computer and go over here and call up AnyLogic as it would be presented to you on your computer. So if you go to the Start menu and you click under AnyLogic 6 University, you'll find it, and you can click on it. And AnyLogic will throw up a splash screen and come up. And what we're going to be doing for this exercise is, in contrast to most exercises, we're going to be modifying an existing, pre-existing model provided with AnyLogic. Oh my gosh. Kurt? Kurt! Okay, well, fortunately, I'm not depending on this, but can you make sure that people's here is firing up okay? AnyLogic, this instructor station the key seems to have gone invalid. Yes. Yeah, well, you're not kidding. Okay, so maybe just make sure others, is people's AnyLogic coming up okay? Yes? Okay, good. So I'll switch back to my own computer where AnyLogic is happily humming along. So we should be able to call up AnyLogic, and the only question is it coming up with a splash screen that shows example models? If so, you should see a splash screen like this, and I'd like you to go to the how-to models. If you don't see a screen like this right away, Kurt, could you tell me when it comes up? What is it showing on their screen? Is it this? It's a welcome, okay. So you should be able to go to the how-to menus on the left-hand side there and select, by scrolling down on the right-hand side, SIR agent-based. Now, some of you may have had this up already. So TAs, could you deploy? 1E? Okay, deploy. Where's Chen Wei Chung? Get him in here. Okay. So help people make sure that they're able to open SIR agent-based here. Okay. So if anyone was using AnyLogic ahead of time, you can go to it with the help menu and call example models. Okay. Okay. Okay.
Yeah. Just so you guys know, by default, when you pull up example models, we'll actually pull up our full example models. So there's a selection below that for the how-to models.
Yeah, the how-to model sort of areas is one of the categories on the left-hand side. And you want to select that first, and then select on the right-hand side SIR agent-based.
Because we have in the example, there's SIR-based, agent-based calibration, which is not the one here. So.
Yeah, there's one called SIR agent-based as opposed to SIR agent-based calibration. Okay? Okay, so what are people getting stuck with? Is someone still stuck? Raise your hand if you're still stuck. Raise your hand if you're stuck. Okay. Okay, it sounds like we're okay shape. Some of you may have been using AnyLogic already, and in general, you can get to the screen by doing help example models, okay? So apologies for that confusion here. Okay, so what we're going to be simulating here is the spread of infection within a population, and I'm going to be going through this right now here. So we're going to be simulating an infection spreading in sort of a stylized space from person to person to person. And as part of that infection spread, we'll see what we call emergent patterns, patterns which are in no way built into the model, but which result from it in sometimes unexpected ways. So I've just opened this model here myself, and you'll notice when it opens, there's several components. There's something called main, person, and then there's some things marked with X's. There are different types of scenarios here. So we're going to be simulating a spread of infection, starting from a single index individual case to the lower right of the space. And there's going to be a natural history of infection each person is going to go through. And if a given person's infected, the infection can spread from them. So let's first of all, let's run this model. And I think based on what you folks are seeing, I'm just going to delete that, because I think this is what you should see here on the left-hand side. Is that right? Yeah? Okay. I'd like you to right-click on simulation and choose Run. Okay, so that's right-clicking on this thing that says simulation. When it says simulation, that's a scenario, okay? That's a scenario which, meaning it's gonna run the model with certain assumptions, okay? And if you right-click on that, you should see something kind of along these lines. Let's rehearse that again. I'll rehearse that again for those just starting along. So this is what should have opened when you click that. If you right-click on simulation and do run, you'll get this screen. And this screen basically allows you to state assumptions, describe how the user interface should be configured, all those sort of things before running the model. So you can kind of get ready to run it in the way you want it. But here we'll just press the button for the default set of assumptions, the default way of showing it. And what you should see is a sort of situation where we have this field of susceptibles, an infectious person starts, and then the infection is starting out from that person. Okay? Starting out and spreading across the space. Okay? As that spreads, we're seeing a growing sort of ring of infection. Let's go see what lies behind this. So I'm going to close this. I close it with this X. Who needs help here? Help?
I had a question.
Sure, okay.
When you mentioned some of the assumptions, I think
Yep.
that's very important.
Yep.
Just to raise
Yes. Right. Good. We're going to be talking about exactly that in the next few minutes here. So I'm grateful to Alex for highlighting the fact that assumptions play such a key role in understanding the phenomena we've just seen. And we're going to be examining how different assumptions lead to changes in that phenomena that may not be obvious. Okay. So great question, and appreciate bringing it to the fore. Any other people need help or have a question right now? Okay. So what I'd like to do now is to dive into what the assumptions are behind this model and look at the pieces out of which it's composed. So I'd like you, on the left-hand side, you'll see this model, and you'll notice it's composed of these three pieces, a sort of scenario that we just ran, but also a so-called main class, which is sort of sets the environment which these agents circulate, and then a person class, which describes a particular agent. I'd like you to double-click on person, and you should see something like this, okay? So what you should see is a situation where we have a person whose behavior over time is characterized by a so-called state chart. Now this is a concept that comes originally from computer science, but the idea is that we have, in this case, an individual who progresses among several states. In this case, it's 3 states, and nod to sort of classic mathematical epidemiology, susceptible, infectious, and recovered states. And there are these lines between them that represent transitions over time. So here we're kind of positing a conceptual structure, sort of how the world works, and we're asking what's the implications of that in terms of broader infection spread. This is how the world works at the level of natural history of infection. the progression of infection for an individual. And we have several stages of it. We have first susceptible, they become infectious and infected, and then they go on to recovered state. So if you double click to get in person, you could see this state. By seeing the model, we saw something like that. Now, what's going on here in more detail is that there's actually a spread of infection between individuals. So if we click on this transition here, for example, we'll see that there's something called contact, and that represents, well, does anyone want to guess what that represents? If we have this transition here, someone fairly new to AnyLogic, what do you think that represents? There's a transition, a person stays within the infectious state, but there's something happening called contact. Why do we need to represent that in a model like this? Yeah, so the infection spreads via this contact. And you'll notice that there's some textured details about this. That contact is occurring with a certain rate, and we'll come back to the meaning of that later. For those who are comfortable with this notion, that's a hazard rate, chance per unit time to contact someone. And there's some action taking place at that point, which will actually end up spreading the infection to neighbors within this space. So each person is going to spread this infection to their neighbors in each of the cardinal directions, north, south, east, and west, okay? In other words, on your screen, up, down, left, and right. If we go to run that model again, and we did that by right-clicking earlier, we saw a pattern like this. Can anyone help us explain what we're seeing here? What's going on here? At a conceptual level, why do we see this pattern? Yeah.
Any infectious disease, you have an infectious person which is going to be more infectious.
Mm-hmm.
So each infectious disease has that what is called in the molecular rate. That's provided in the ideal circumstances. The circumstances of ideal situation that we don't put in so provided that that infectious disease connected person to person, that certain infectious disease enters from person to person, that's certain paths. So some infectious disease actually do not from person to person infections.
Right.
We can really use that example to underline that. So, but at certain point we have a point such as an individual which introduces an infectious case there. So at some point all of those infections will develop the disease until the reach a point where it's going to know before this saturation of all the infections get infected with the dynamic of the if you put some measures that prevent this spread, but you could modify the direction to find to have more purpose prevention measures we actually stop the outbreaks from spreading
Great. So couldn't have put it better myself, but what you just had there is a sort of mini primer on basics of mathematical and computational technology and sort of the theory behind infection spread going from the level of a person to the level of a population. We started here with an entirely susceptible population. We have an individual who started infected and spread that infection out to their neighbors. What's this? And up here we'll find that there's red, you know, the infectious individuals as it spreads out. And then there's a gray to represent the recovered individuals. Could people help me understand what's going on here? Why is it we see this sort of big blotch of gray and then a red ring around it, surrounded by this sort of this yellow? What's going on there?
So those who are recovering and developing the immunity. In fact, I would say from a physician point of view,
Yep.
you can be recovered when you can die.
Right. So removed is the term that's sometimes used for both. Yeah.
I think it depends on the severity of the disease. If
that?
And the 762 is. In the dynamic of that outbreaks, once you are had a disease, so you will not be able to, you won't get it again, because you are kind of in the clear, hopefully you will recover.
Right. Okay, so these individuals are now recovered. It started, where would you think, looking at this, where do you think it roughly started? Where did the infection get seeded? Anyone want to guess? Is it up here? Is it here? Where did it get seeded? Really in the summer, probably around this sort of gray area. It actually is fairly randomly chosen where they got seeded originally for each successive run, but probably started somewhere here and spreading out. Why do we see these reds clustering around here on this border? Anyone?
Driving the propagation of the outbreak, it's susceptible to the infection.
Okay, very good. So these are the individuals who have been recently infected, and they're the ones who are still spreading that infection. So it's spreading up kind of like a wildfire, right? We have an initial point where the fire takes, and it spreads out. The parts burning at any one time are sort of this one-dimensional ring around the original point, or a fairly thin slice. This area has been burnt already. It's so burnt that even if there are a few susceptibles in there that have survived it, there's not really a chance that the fire will be able to sustain itself there. The fire is sustaining itself where there's fuel, right at this periphery, and it's spreading outwards because it can't burn in these areas anymore, and the areas get consumed, so it's spreading outwards. So let's examine this at a little bit more of a quantitative level. So I'd like you to right-click on that, again, on that scenario here, and select Run again. It's just one way of many to run things in AnyLogic. You could also do it through this button up here. And I'd like you to press that button to start the execution. I'd like to suggest that you, while you're running it here, and I'll do this along with you, that you actually try adjusting the model interface. You can do it either before and request that model time is shown here by sort of clicking down here, or once you actually start it, you can do the same thing. So with this little customization thing, you can make sure that model time is selected. Now, each of these dots here is one individual, and it's spreading across the space. And this requires quite a bit of effort to simulate. This is 250,000 individuals within this space. And we're going to just watch here, given that we've requested that time be shown. We're going to watch and see roughly how long it takes to reach the upper quadrant of the screen, the upper side of the screen, okay? So we're running this here, and what we see is, again, this kind of area that's burnt. That's a set of recovered individuals. The infection can't propagate in these areas. It's just not efficient enough. There's too many things already burnt, too little fuel for it to spread. This is where the action's at. This is where the spreading is going on. And it's going to move across the space in a sort of general way. Okay, so here it's moving upwards towards the top, and we'll time it so that its periphery reaches the top of the screen here. I've got recording going on in my, so it may be a little bit slower than your machines. I'm not sure how fast yours are going here, but we're almost there. Okay, so the time required to reach the top of the screen looks like it'll be somewhere around, what, 300, something like that. Okay, yeah, it's just about 306, okay, yeah, so around between 305 and 310. I'm going to close that window by clicking on the X, okay? So how long does it take to reach it? Between 305 and 310 here. We're going to compare this situation with assumptions regarding the progression of infection with different assumptions, okay? So I stopped it by clicking on the right, the X here. You could also stop the actual execution, but keep the window up by pressing this red button here. Okay, so we're going to go modify this model. Now, in the process of doing this, you may get a warning, okay, from AnyLogic saying, oh, you're modifying a built-in model, I don't know what to do. And you can ignore that. So what I'd like you to do is we're going to modify it to change some assumptions. Alex highlighted the importance of these assumptions as part of this. So I'd like to right-click on the simulation and select copy from the menu. So like normal, I'll follow this around. So right-click on the simulation, select copy. We're going to create a new scenario, okay? Having done that, we're then going to right-click on the whole project and select paste. This is just one of many ways we can do this, but select paste here, okay? Basically, we're doing this so that we can retain many of the assumptions that were in the original and just tweak one or two to do a very, very careful experiment. Okay, so how did I do this? I right-clicked on the simulation, did copy, and then right-clicked on the entire project and did space. Who needs help here? Help? Help, okay. So your screen should look something like this. There should be a simulation 1 where it's showing an X here, okay? And I'd like you to change the name of the experiment, of that experiment, the new experiment that appeared, where it says simulation 1. I'd like you to change it instead to be slow recovery, okay? We're going to slow down the recovery here. In other words, people are going to be infected for a longer period of time. And the second thing I'd like you to do, while you're naming that, by the way, this highlights a point. In AnyLogic, you select something, and then there's this properties window down at the bottom, which allows you to change things about that selected item. In this case, we changed its name. And we're going to need to actually select sort of what model it's running. In this case, we say, okay, it's running this model indicated by main here. Okay, that's just sort of a nod to it. Where is that going on? Well, again, we selected it. We selected the general tab, and then we typed in slow recovery. Okay, and we needed to select main as what model to run. Okay, who needs help here? Help? Okay, so main represents sort of the general stage on which the agents circulate, whereas person represents a particular, it describes personhood, it describes personness. Main describes the overall simulation, the overall sort of model itself, okay? Now, some AnyLogic models might have several alternative kind of models as pieces of it that you may want to sometimes run one, sometimes another. And so when you have an experiment, you could say, what should I base this on? In this case, main is the only really reasonable choice. It wouldn't really make sense to base it on person, okay? But sometimes we may have several mains which represent kind of alternative models with different structures, say, or a different theory about how they work. Okay, so I just selected main here, and now what we're going to do is we're going to make different assumptions associated with this. But who needs help in this? Who needs help? So
What happened if you select person?
sorry.
What happened if you select person instead of name?
What happens will be something unusual. It will not be terribly helpful. So let's go do it. One of the best ways you can become comfortable with AnyLogic is trying things. Let's go select person. So suppose we were to select person here. It encounters discomfort. We don't wish to select. The reason we can do this, these are experiments, these are scenarios. We want to try running the whole model with different assumptions. And the thing that sort of coordinates the whole model, it's the stage in which the various agents were individually types of persons whose personhood is described by person. They're circulating within this main space. That sort of coordinating the populations of agents in this case. In this case, it's just one. And so really it only makes sense to specify a main class here. The reason AnyLogic gives you this flexibility is because we may have several alternative kind of variations of the model here, a main one or a main two, alternatives that we may sometimes want to use one, sometimes the other, okay? So anyone need help with this? Okay, help? Okay. Okay, so we've just done slow recovery. Now the other piece of this is we need to specify the average, or we need to specify the whole reason we created this new scenario is we want to describe an alternative set of assumptions, as Alex indicated earlier, that's so key. So what we do is we select that slow recovery, so the properties for that are shown. You go to the parameters tab. Okay. It's actually exposed elsewhere too, but perhaps it's conceptually easiest if you go to the parameters tab, okay? So here's parameters, and you'll notice that the assumptions are spelled out there. For example, how long is the illness duration? How long do people stay infected? What is the contact rate between individuals? How frequently are they contacting each other? On a per contact basis, per so-called discordant contact basis between a susceptible and infective, what's the chance that infected will transmit the infection to that susceptible? These are the assumptions which we can put in here. For this slow recovery, we're going to go from an average illness duration of 15 to an average illness duration of 50, 5, 0. So we're going from 1, 5 to 5, 0 for the average illness duration. How did I get here? Well, again, I selected, this is the scenario, and this is properties window. It shows me characteristics of that scenario, the sort of properties, the traits of that scenario. And then I go down here to the parameters tab of this properties window, where I can specify the parameter settings. These specified, ladies and gentlemen, are assumptions, okay, for this scenario. Okay, are people feeling comfortable? Who needs help here? The TAs stand poised for deployment. They're ready to help you. Okay, help is needed here. Oh, question. Okay, it's a good question. So there is a time unit imposed, and if we actually go here and we go up to the model as a whole, and just click on the model as a whole, you'll notice the time unit is specified as days here, okay? AnyLogic supports a variety of time units at different scales. What's important here is that the time unit be consistent across the entire model, okay? So you can have a model that, whose time units are in centuries. As long as you're consistent across the model, and keep in mind very clear that you're dealing with centuries, that's fine. You can use variables that have different times in them. Say you have a model that simulates in years, but you have length of infection in days, but you need to convert it from days to years before you combine it with the others. Okay, so other questions about this? Need help? Help here? Help? Okay. Yes.
How does the scent infection work? So, like, how does it run
We're going to be talking about that later. The answer is that there's several different options. You can specify send it to this particular neighbor, say that you choose directly, or you could send it to a randomly chosen neighbor in my space. It's a direct neighbor, or send it to anyone in the entire space. You can also send it to a neighbor in the network that I'm in. Okay, and all of those have easy ways of describing them, and we'll be talking about this later this morning. Okay, great question. Great question. Other question? Okay, so ladies and gentlemen, so we've just created a slow recovery, and we've slowed down the recovery from 15 days to 50 days. So in other words, they're ill for over 3 times as long. Now, approach naively, what would you think that this would mean about, say, the number of people that ultimately get infected?
Clearly, if you assume
Mhm.
the average duration of
Yeah.
instead of translating to the infertility period, so things that I have to know.
Yeah.
They element of the fertility period down so that there may be more infection before they get it, 3 days before they get it,
Yeah.
and eat the early days of the infection.
Sure.
Then that period fertility can go down as
Sure.
regulated.
So something like HIV, there's this acute phase early on following infection by the virus where there's the much higher risk of infection.
I don't know whether that model really is only will work for infectious diseases that are considered human parts, whether they like nuclear needle.
Yeah.
Some sort of contact with not used.
Right.
There's a disease that needs some sort of
Right.
considered as doctor.
Needle sharing or sexual contact, some
There is a certain disease that has a very different mode of transmission. I think looking at this, I feel that that one may be after infectious disease which they use
Right. Okay, so those are good comments, and we'll see some textured models of diseases of other sorts in the context of this boot camp, including sexually transmitted infection and TB, for example, which are rather different. Yeah, in the back. Okay, so we'd expect a higher prevalence. Scott.
I would argue that you're not going to see any change in the amount of time it takes for the infection to spread.
Okay, and why would that be?
Because right now, the person stays infected for 15 days.
Mm-hmm.
On average, he contacts one of his neighbors every day to try to infect him.
Right.
If he stays ill longer, he still cannot infect anyone but someone adjacent to him.
Okay.
Therefore, I don't think you should see any real change. What you'll see is that the band of red, as it goes through, should be thicker, and that's what
Okay.
the only change I think you'll see in the model.
Okay, so anyone want to disagree with that? So would the infection spread faster? After all, there'll be, as was noted in the back, more people infected at a given time. More people could transmit the infection to somebody. Does anyone want to argue that it should therefore spread faster? Because after all, there's more people who have that ability to transmit infection.
Yeah, they could, because if they are moving out, obviously you will have the chance to infect others.
Okay,
If
so
not, then don't.
so some reasonable sort of questions about this. Yes, in the back.
Well, it depends on the reproductive time or the reproductive number
Okay.
and contact rate. I would say reproductive.
Okay. No, without going into it in detail here, for those from mathematical epidemiology background, if we have a classic SIR sort of characterization of a situation with random mixing, which we don't have here, but we have a basic reproductive rate of sort of this is the contacts per unit times the chance per discordant contact of transmission, and this is the duration of infection. And that would suggest that R0, the basic reproductive constant, should be higher. But this is an abstraction. This is based on a set of assumptions. And we're going to see how well that applies here in terms of sort of the overall spread of infection, how well it actually will change things. So let's run this. We created this alternative scenario. We changed the assumptions. Let's run it. And see what happens. Let's see how it jives with some of the statements made. So I may have screwed up on that. Let's go run it here. Okay, here we go. So what do we expect to see different? What's a visual difference that we should see? What's a visual difference that we should see?
We can see it on your chest.
Okay. What's the difference that we should see visually? Sorry? More reds. Okay. At any given time, there should be a thicker annulus, a thicker sort of ring. Oh gosh, you know what? I deleted it. That was the original one. So I was keeping you honest there. Did it look thicker? No. So I was wondering. Okay, this is interesting. Okay, so fortunately I bought myself more time. So how should this be different? Well, we should see a thicker ring. It's taking time to. You notice that in quite a bit of time, there's a lot of action going on, a lot of moving parts, a lot of people getting infected, sending these messages to infect others, and you can see it's actually quite a bit of a thicker ring. The question is this going to get up here? This is something Scott was trying to address. Faster, slower, at the same rough time as the original one? Anyone? About the same. Why is that? Why is that? After all, there's more people infected. Look at all these people infected here. Okay, the contact rate is the same. Where is the contact taking place here? Okay, is there contact between a susceptible infected occurring in here? Where is it occurring? At the periphery. How about all these people here? Are they spreading the infection actively? No, they're infected, but they're not actually contributing to the spread of infection. The fact that all these extra people are infected is not really contributing to the speed of infection spread.
Is it because they are infected? Well, I mean, I don't know whether whether you would use the infectious versus sick.
Okay, yeah. In this case, this is infected. They are infectious, but they're not in contact with. They're not engaged in discordant contact. They're contacting people, but all the people they're contacting are either recovered, the gray here, or they're red also. They're infected right now, so they can't spread it. Okay, so without going into it in detail, the infection does not actually spread any faster. Okay, folks, so we've just seen how we could change the assumption about a model in a particular scenario. Question, yes?
So based on that equation over
Yeah,
there,
yeah.
it's like the R naught should be. So is that because of the spatial orientation of the
Right. So, excuse me. So this equation for R naught for the basic reproductive constant or basic reproductive number, as it's termed, is describing, for those not familiar with that quantity, the quantity describes the average number of people that would be infected by a given index infected, a given initial infected, and an otherwise totally susceptible population, right? And there is, in fact, a pretty good match of this to what we, excuse me, you have to be careful there. So this formula for R naught is based on a certain abstraction that's associated with classic mathematical epidemiology, where we assume random mixing between people. In other words, there's mixing within the population, which means that a given person could come into contact with and infect, let's see, anyone else in that compartment of the population. In this case, it's in the whole population. So the idea is they have some number of contacts per unit time, which are with different people without sort of discrimination as to who they're in contact with, and each such contact confers a chance of infection of beta, and that's, so say 50 contacts per day with, each having a 50% chance of contact, so an average of 25 contacts per day that transmit times the number of days they're infected. But what this is positing is that they are contacting people willy-nilly across the entire population. Here in this model, we have contact not occurring willy-nilly, but with neighbors, very structured neighbors, north, south, east, and west. And we can only infect so many of the neighbors before they're maxed out, before they're saturated. So we could have more and more contacts going on, but if we're going to be infecting those neighbors anyway, at some point, we can't infect more than 4 neighbors, and that's it. And so the limits of this become obvious because, this may be an okay approximation if beta is very, very small, or if C is quite small, and we're not saturating the number of people around us. But as these quantities rise, this approximation becomes weaker and weaker, and so it doesn't carry over well to this sort of model. This, in other words, is based on a simplification of reality, assuming random mixing that doesn't apply well to this structured case where there's locally, where your ability to infect someone is highly dictated by your relative positions. Does that make sense? Yeah. So,
Side question.
great.
So, from the specific example,
Sure.
R naught of measles is 70, 80.
Yes. In many modern contexts, that's right. Yeah.
R naught of pertussis is pretty similar.
Yeah.
So those two diseases have some with different mode of transmission. They're airborne.
Yep.
One is those target droplets.
Right.
So the difference between these two is that in those target droplets, I can define it in this case, I can transmit it as
Yeah.
if I'm an airborne, I can transmit it from the air.
Right.
R0 is the same, but conceptually, the dynamic of the
Indeed.
cluster of the outbreak of measles pertussis, so even though R0 is the same,
Yep.
I would provide measles because both of them are very infectious.
Yeah.
So, but the measles has that additional transmissibility that makes it easier. How does it reflect
Yeah.
R0 value, which is not,
Yeah.
can you capture that in the model?
Yes, we could. And we're going to see models later which allow for longer range transmission. Here we're dealing with a very, very stylized situation where you're transmitting it purely to immediate neighbors. You can imagine a generalization of this model, which, for something like measles, which has this longer range transmission where you could transmit to people in a broader range of the space, for example, or with some measure of that transmission being have more random mixing, say, the people that are in the bus as you ride it to work in the morning or something like that, in addition to those, in cubicles across the floor or what have you. So we could allow for non-local transmission or less local transmission, and that's something we'll see with networks later today. So great question.
Where do you define that number of persons, the maximum number of persons? Because here we are saying, well, we are infecting everyone around you.
Good.
Where do you define
Where is that actually described? Well, it's a great question, and what you'll actually see here, we'll unpack this a little bit later in the morning, but what you'll actually see here, is that when we send the infection, this is really where it comes down to. When a person is infective, that is infectious, they can communicate this infection to another person. They do so, the computational mechanism is called sending a message. They say, hey, you're infected, okay? And the way this is done is it's sent to a random neighbor, and in this case it means a immediate neighbor. Now, to further unpack it though, there's a thing called the environment, which we'll be meeting later as well. And in the environment, there's an indication for who's considered your neighbors, okay? So specifically this is neighbor type, Moore versus Euclidean, for example, where Euclidean includes some individuals who are, and not just the cardinal directions, north, south, east, west, but also northwest, southeast, southwest, and northwest. And those individuals be considered as well. There's a generalization of this yet. Further, if we wanted to make use of a broader spread where we could have a distance-based network which allows us to reach out even further in distance, okay? And consider a broader set of people, yeah. So, hope that begins to address it. We'll be getting to a lot of these issues later. So, just trying to have a very simple example here. But I'm glad I welcome the sort of textured questions. What I'd like to highlight to you, though, is that what we've done is we've modified the numeric assumptions about this. Let's modify a different type of assumption, to wit, an assumption concerning the natural history of infection. So Alex mentioned earlier pertussis. Pertussis is a very interesting communicable disease these days because, among other things, there's increasingly recognized to be a lack of lifelong immunity conferred by vaccination. So there's recommendations these days for multiple vaccinations within an individual throughout early stages of their life, and even a cocooning strategy for them during the reproductive years to shield them in the context of the family, and help lower the risk that they'll get infected by children, or they'll infect children by capturing it from someone else. So we're gonna posit a situation where we can lose immunity now. And Alex was referring to this earlier. Situation where immunity is not permanent, but it can be lost. And there's many reasons for this. Sometimes it's due to pathogen evolution. So the outer membrane protein gonorrhea, for example, mutates at quite a fast rate. HIV is another infection which is also known to mutate, but flu is probably more notable in the sense that you can get reinfected in separate years due to different strains or mutations within a strain. So what we're going to do is we're going to add a transition for waning of immunity. So to do this, folks, we're going to be modifying the structure of the model. That's in contrast to just running the model with different assumptions about parameter values that we just undertook. So to this point, we've been sort of living in the comfortable space of just changing parameters. Now we're actually going to modify the model. So what I'd like you to do is I'd like you to double click on person. So we need to go to person, look at the person class again. TAs, brace yourselves. So double click on person, and I'd like you now to add a transition. How do we do that? Well, we drag in from the state chart area of this palette on the right-hand side, we drag in a transition. If you can't see that state chart area, you may have to expand the palette. For example, it may be that it's that this palette is not visible, in which case you could do view palette and make it visible, but it's down here in this state chart area. So if you drag in from transition, you should be able to drag it so it comes from recovered. Okay, so TAs, who needs TA help? Who would like help right now? So we'd like to drag that in, and we're going to have this transition go from recovered to susceptible. You notice when you drag it in, if it's connected properly along one of its edges, you should get a green dot. Okay, that green dot indicates that it's connected. Okay, so I just connected this logically from recovered to susceptible. How did I do this? I dragged in a transition, and I connected it. Let's rehearse that again for those who are following. So I drag in a transition, and I'm just going to satisfy myself with leaving one edge of it. You'll notice it's green there, indicating a proper connection. I'm going to drag the other edge up to susceptible, okay? Just like that. And what I'd like to do is to name this transition waning immunity. Who needs help here? People need help. Who would like to step forward? Who needs help? The TAs are poised. Okay. So we should call this waning immunity, this transition. So the transition is selected, so its properties are showing, and we should name it waning immunity. And I'd like to give this a waning of immunity with a timeout of 100, meaning that exactly 100 time units after someone recovers, their immunity wanes. Okay, now I'm gonna, so, you know, over the years I've come to realize my limitations. And one of my areas of acute awareness of my limitation is in the aesthetic domain. this transition currently passes through the infectious state. So I'd like to route this transition around. So we can do this in AnyLogic by double-clicking on this transition, and you're going to have to do this carefully. So you're clicking on the transition itself. Oh, come on. By double-clicking on this transition, you can put what's called a handle in it, and by dragging the handle, you can kind of route it around that place, just to make it more visually clear that it's going from susceptible back to recovered. Folks, you should be sure that there's a green dot on each edge of this. Otherwise, it's not connected. If it's close, it's we're not playing horseshoes, and so if it's white here, it's not connected. It needs to be dragged up here to connect. Okay, so who needs help here from a TA? The TAs are mingling and stand ready to help. Who needs help? Okay, so folks, I've added this transition. I dragged it from here. I connected it up to susceptible, and I created it with a timeout of 100. So that means exactly 100 days after someone recovers, they'll go back to a susceptible state. Okay. Okay, we have modified the model here, the model structure. We've modified our sense, ladies and gentlemen, not just about how long things happen to take, not just our assumptions about that, but how things work in the world, sort of the natural progression of things. We've changed what we posit about the sort of the natural history of infection for this condition. What I'd like to pose to you, ladies and gentlemen, is how will this change? So we've run this model. We've seen bands, thick and thin. These bands of annual systems. Now that we have waning immunity, what are we going to see different? How will what we have seen differ now that we have waning of immunity? Okay. And why would there be a second wave of infection? Help me unpack that.
We have recovered patients, and now they've lost their immunity.
Okay.
Able to be infected if there's infection surrounding them.
Good. Okay. So, very, very well stated. I'm just struck by the prescience of some of the comments I'm hearing here and the depth of some of the comments. Really welcome. Let's go, ladies and gentlemen. Let us compute and let's see this. So let's right click on simulation and let's run this and let's see how this jibes with our guesses. So first, I'd like you to run. We have two scenarios. You'll notice these scenarios are still there. They used to be run with a model which had no waning immunity, but now we've modified the model structure. So when we run them, they're going to be running with this updated model structure. It's important to keep that in mind. Save early, save often, version your model. Save successive versions of your model so you can go back to earlier versions if you're modifying it in substantive ways. It's one of the lessons, in case you want to go back and see some of the earlier results. Okay, so I'd like you to right-click on the simulation, and we should be able to run this simulation with this modification, okay? So here we have a running of infection. Does anyone see anything different yet? Okay, what's different? Okay, so this is spreading out here. I'm running the original. Okay. Yeah, should have made that. Okay, so help me, give me a narrative for what's going on here. What do we? So something visually is very different. Why? Okay. Great. So where are these small infections coming from, these internal infections sort of in this area? Where do they come from? Like, how can one of these susceptibles get infected? Through what means? Like, why is there a thin nucleated here, here, or here? It's because well, you'll notice there were still people who remain infected, these occasional infected. See this one guy here?
Yeah, or this is a new introduction, alternative
residual, yeah.
You can easily have a second wave triggered by something.
Indeed. So exogenous introduction,
I will be able to like it simply
yeah, migration. Correct.
I think the thickness of that
Yeah. Okay.
I suppose the other question whether you like the waiting immediately
Uh-huh.
in the context is what we've seen in North America makes more of a waiting
Indeed.
concept of waiting
Yes. It's after vaccination.
I think you even after somebody get a disease that it's more vaccination
More quickly. Yep. No, that's my understanding, and certainly there are many communicable illnesses out there. We mentioned some earlier, gonorrhea, flu, for example, where there is even after natural exposure, there's a waning of immunity. Or let's put it this way: there's a waning of practical immunity to getting infected again because the bug is mutating in the population. So we just saw that. How would it be different for a slow recovery case? Anyone? What did we see? What was the distinguishing feature of slow recovery visually before? Okay, more red. So what's going to happen now when we have waning of immunity in the context of slow recovery? So be reinfected a lot quicker. Okay. So at a visual level, will this be similar to what we just saw or different? Okay. Okay. So here it's propagating out. There's a lot going on here. Your machines are probably quite a bit faster than mine. Okay, here's a person who's susceptible there. And what's going to happen? Well, very, very quickly those people end up getting reinfected. And you don't see the sort of really very, very pronounced waves of infection like you might in something like diseases which have very rapid waning of immunity. Okay, so there you'll see this kind of intermixed wave there. It's not really nearly as pronounced. Okay, one final question. Suppose we wanted to go and make the waning of immunity have a longer time between when someone recovers and when the immunity wanes. Let's make it not 300, but say not 100, but 300 steps. How would that change things? So I'm going to make it 300 times steps and run it with not the slow recovery, but regular recovery. How will that change things? Okay. So now we have this long time, 300 time steps between when they recover in the first place and when the immunity wanes. So now you've got the infection propagating out. But the first individuals to sort of lose their immunity won't appear for a good long time. And at some point, what's going to happen? Ultimately, what's going to happen? If that, say 300, maybe it's 200, maybe it's 500, at what point, what will change qualitatively?
You will have a yellow.
Yeah.
It has to be reestablished.
Exactly.
So you will have a reestablished pool of susceptible
Okay. Very good. Very good. So that's exactly it. So you're going to have the slate is cleared by the time 300 time units appear. you're gonna have basically all of these individuals, these residual individuals who remain infected cleared away. And you're going to have a situation where, excuse me, this is for some reason not visible there. There we go. So time 230. Remember, we have a time till waning of immunity of 300 here. So this is a very, very extreme case. The first person to secure a waning of immunity has yet to appear, and these last residual infected individuals are disappearing rapidly from the superior. And here we go. So we're approaching 300. What should we expect to see now? Okay, we'll start to see susceptibles quite quickly. And there these susceptibles come. If I ran this long enough, what would I see? It'll be all yellow. The entire root yellow. It'll be back to original state. The infection is long forgotten. Civilizations have risen and fallen, and we now see the world is fresh again, waiting for new infection. Yeah.
So I assume that the conversion based on the agents being non-coding will make a difference in these agents or moving.
It would most certainly make a difference if they were mobile agents. Why would it make a difference? I'll pose that to the group. Suppose these agents were mobile. Suppose they were not stuck in place, they were not located in fixed positions, but they were instead moving about the space.